Okay, now work through an example problem that involves the work done by a spring, also involves the work done by gravity, work energy theorem, and then turning the work energy theorem around to find the speed of an object, how that relates to its displacement. Okay, so we have a mass that is falling onto a platform supported by a spring. The mass is 250 grams, so that is 1/4 of a kilogram. It is attached, the platform is attached to a spring with a stiffness of 2.5 newtons per centimeter, which, going to our MKS units, is going to be 250 newtons per meter. And the spring displaces by 12 centimeters before the falling block comes to rest. So 12 centimeters is a displacement of 0.12 meters. We need to be clear and thoughtful about what our initial and final states are going to be to apply conservation law for energy. So for my initial state, the mass has just made contact with the spring. So the instant of contact, or you could say right before contact. And the spring hasn't done anything yet, so it's still at its equilibrium extension. And then my final state that I'm going to connect through the conservation of energy is when the block has compressed the spring by 12 centimeters. And we want to find a variety of things. The first is the work done on the block by gravity. So let me draw a little diagram for our block. So the force of gravity on the block acts straight down. That's also the direction that it displaces. And the force of gravity is constant. So we can get the work of gravity pretty simply. It's going to be force of gravity dotted into the displacement using the dot product. And since the force is constant, this is the same amount of work over the first little bit of delta R as over the last bit of delta R. So I can express the work done by gravity as just the magnitude of the force, which is the weight, magnitude of the displacement, so delta R, and those two are pointing parallel to each other. So I have a cosine of 0 degrees. And cosine of 0 degrees is just 1. So the work done by gravity, I put in my numbers, 0.25 kilograms on Earth, so 9.81 meters per second squared, goes through a displacement of 0.12 meters. And when I calculate that, and I'm going to keep some digits here, I get 4. So everything has, well, that only has 2 digits, so I'm keeping an extra digit because I happen to know that in my near future is a quadratic equation. And taking that square root in the quadratic equation, I want to know some of these terms with a few extra guard digits. Okay. The second thing that we're asked is the work done on the block by the spring. Let me start off with a similar diagram. At one instant in time, the spring is pushing up. So there's a force of the spring while the block is displacing down. We need to remember that the force that this spring exerts is not constant. It starts off exerting no force, and the more and more you compress the spring, the greater and greater the force is. It's from Hooke's law. So the force from the spring is not constant. So as with the force of gravity, we could just, since the force of gravity on the block was constant, the displacement was just some value, we could just multiply them together. And we can't do that here because the force exerted by the spring depends upon what the displacement is. What we can do is go back to our definition for work and potential energy. And that is that the work done by the spring is minus the change in the elastic potential energy. That we can calculate because we have the beginning and the starting points. And Hooke's law gives us a force that's conservative. Conservative forces have an associated potential, and we can get the work done by the spring from the work potential energy relationship. So I'm going to have minus, and then in parentheses, half kx final squared minus half kx initial squared. And we took that to be our 0 point. So the work done by the spring is going to be minus k over 2 x final squared. Putting in values, the work done by the spring minus 250 newtons per meter. It's the stiffness of our spring. I have our factor of 2, don't want to forget that. And then x final minus 0.12 meters squared. Minus 1.8 joules. So looking at our energy budget for this problem, the force of gravity is going to slightly speed up the block as it falls 12 centimeters, and then the spring is doing a much larger amount of work to slow down the block, hence the minus sign. It's reducing the kinetic energy of the block. All right, the next thing we wanted to find, I'll go to a new sheet of paper here, is what is the speed of the block right before it hits the spring. So speed of the block just before it hits the spring. So the net work done on the block is the change in kinetic energy of the block, so it's the work energy theorem. Change in kinetic energy is going to be final kinetic energy minus initial, and in our final state the block was at rest, so it had no kinetic energy. What forces are doing work on the block? The spring and gravity. So the net force is just going to be the work done, the net work is going to be the work done by the spring plus the work done by gravity is going to equal minus the initial kinetic energy, which is equal to minus a half m v initial squared. We want to solve for the speed, and notice since we're asked for the speed, we only need the positive root when we flip this around. If we were asked for velocity, there would be two possible values, plus minus, but speed can't be negative. It's the magnitude of the velocity vector, so I'm not going to worry about the plus minus. Rearranging this equation, I'm multiplying both sides by 2, dividing both sides by m, and flipping around the minus sign. I have minus 2 times the quantity of the work done by the spring plus the work done by gravity, so the net work, divided by the mass of the block, all square root. If I put in values for that, I'm going to have a minus a 2. I have a minus 1.8 joules. I had our plus, the work done by gravity was 0.294 joules. We have the mass of the block, 0.25 kilograms, all square root under the radical, and that gives us 3.47 meters per second. I put that in my calculator. Okay, and then the fourth part is more of the head scratcher. What happens if we double this initial speed? So it's not 3.47, but twice that. So initial speed doubles. What is compression of the spring? So what is x final? So at 3.47 meters per second, it compressed the spring 12 centimeters. If I double it, I'm pretty sure it's going to compress more. But how much more? Getting an exact answer takes a little bit more thought. So the work done by gravity, that's going to be proportional to how much you compress the spring. But the work done by the spring goes as not just the compression squared. Okay. So we're going to have a quadratic equation to solve to find what's the final compression of the spring. So that is the net work done by the spring plus the work done by gravity is equal to minus a half m the initial squared. Move the kinetic energy term to the left-hand side. Work done by the spring, work done by gravity, plus a half m the initial squared equals 0. And let's write out what these works are. So the work done by the spring minus a half k x final squared, work done by gravity plus mg x final, and then our initial kinetic energy, a half m the initial squared equals 0. So this is a quadratic equation to solve for x final. Our a in the quadratic formula is going to be minus k over 2. B is the weight, mg, and c is the initial kinetic energy, half mv initial squared. All right, our quadratic equation, x final is minus b plus or minus quantity b squared minus 4ac. It's all under square root, and that's all over 2a. Substitute in what those are. X final is equal to minus mg plus minus m squared g squared. I will have a minus 4 minus k over 2, and then the c term is going to give me a m, the initial squared, over 2. All that's under a square root. And then in the denominator, I've got a 2 times minus k over 2. So I'm going to get a clean sheet of paper here. I'll clean that up. I've got x final equal to minus mg plus minus m squared g squared plus k m the initial squared, and in the denominator I'm going to have that resolves itself to a minus k. Clean it up a little bit more. X final is going to be mg over k, plus minus over a minus, so it's just going to be plus minus 1 over k, m squared g squared plus k m v initial squared mg over k. When I evaluate that, it's going to give me 9.81 times 10 to the minus 3 meters, so just about a centimeter. All the rest of this, the 1 over k, and then the radical, that when I evaluate it, I get the following: 0.2197 meters. So our possible values for x final, now I'm just going to round them to keep two significant figures. I'll get a 23 centimeters, so 0.23 meters, and I'll get a 0.21 meters. All right, now let's talk a little bit about what these correspond to. 0.23 meters is the story if the block started with its double initial speed of 6.94 meters per second and is directed down. So that gives us how much it's going to compress the spring to bring the block to rest. That is also the direction that gravity is helping to speed up the block. If instead it was 6.94 meters per second directed up, and the block was somehow tied onto that platform with the spring, then I will stretch the spring by 21 centimeters. And here, the spring is doing work to slow down the block, and gravity is also doing work to slow down the block. So two possible answers depending upon that initial speed when the block is first in contact with the spring. Does that speed correspond to motion directed down? So I'll get this compression, or motion directed up, which will give me the spring stretching out by 21 centimeters.